Good afternoon, everyone. My name is Jeffrey. I'm currently a 12th grade student at York Community High School, all the way over in the United States in the Chicago area. Today, I'm going to be presenting a new approach for logical reasoning with NLP AI. Now, first of all, why do we even care about logical reasoning at all? Now, the typical path to benefit for a natural language processing AI model consists of starting with some training knowledge, typically in the form of a corpus of text, for example, a compilation of books or perhaps Wikipedia, feeding it into the AI model and extracting some sort of benefit from it. So today, it looks like taking your training data, the AI identifies some directly related information to your prompt and simply regurgitates it into its output, adding some filler text either from the prompt or from its prior knowledge to make it look more natural. Now, the main benefit here is just time-efficient information retrieval. Now, this is really great, but we could do even better than this. If we could take more contextualized information, then we can do, again, the same regurgitation, but add the extra layer of rational synthesis. Now, this rational synthesis creates inferences and conclusions that approach a more commonly accepted definition of intelligence. Now, I've been talking about logical reasoning, and we can take a look at what exactly I'm trying to get at here with a sample question. So our context, or the knowledge that we looked at previously, will look something like this. I'll read it for you. It says, in jurisdictions where use of headlights is optional when visibility is good, drivers who use headlights at all times are less likely to be involved in a collision than are drivers who use headlights only when visibility is poor. Yet Highway Safety Department records show that making use of headlights mandatory at all times does nothing to reduce the overall number of collisions. Now, we could ask the question, what fact, if true, most helps to resolve the apparent discrepancy in the information above? Now, I fed this into an LLM, and as a note, not all LLMs will make the same error, but many of them will still have this regurgitation response. Highlighted in blue, we see effectively paraphrasing what we directly fed it through the context and adding some filler information at the top and bottom that adds no real value other than simply attempting to answer the prompt. And here, there are actually some errors. It notes a point about daytime hours, which has absolutely nothing to do with our prompt and is not relevant at all to our context. So this is completely faulty, both logically and factually. Ideally, we want a response that looks like this. This is human-generated, and it's very short. It says, only very careful drivers use headlights when their use is not legally required. Here, there are no logical faults, there are no factual inaccuracies, and this answers the prompt very directly. This is what we want AI to look like. Now, to actually get there, we have to take a few baby steps. There are other approaches to creating this complex rational thinking sort of model, including prompt tuning through ideas like chain of thought processing, or directly encoding these logical rules in things like graph neural networks. But today I'm here to present an alternative approach. If we break down this larger, complex, and confusing model into two submodels, the first model taking in the context and our non-trivial prompt and generating a wide array of possible responses, most of which are likely to be bad, but hopefully some of them will be acceptable and considered good, rational responses. We can take a second model that effectively vets these possible responses and identifies which one among this finite list is the most rational, per se. Now note that this second model is actually just multiple choice. And we can specifically define what we want our model to do, which is that given this context, a question, and multiple plausible answer choices, all we need to do is determine the quote-unquote correct or most rational answer choice. Now, to examine this question more theoretically, the forward approach, the approach used most by students, including myself and my peers, is to look at the question and think about some sort of plausible response, a rational response, and just hope that that's one of the answer choices or very close to one. But this doesn't work all of the time. And in fact, if you don't entirely understand what's going on, this approach is completely not feasible. Now, when intelligence fails, we can rely on intuition. And instead of looking at our forward approach, starting with the question, we start with the answers first. And each answer will have some level of apparent wrongness that you can feel with relation to the question and the context. And if we can create this sense of apparent wrongness in an AI model, then all we have to do is select the answer that minimizes this wrongness value. And the key idea is that we only care about the relative correctness of answers, and we could not care less and can completely ignore the absolute accuracy of each of the answer choices. Now, the way we actually implement this broad theoretical idea is through spatial representations. So first, we take our natural language prompt, including the context, the prompt, and all the answer choices, and because these are difficult to interpret, we have to convert them into something that's numerically interpretable. Now, we know from many natural language processing models, we can convert these textual inputs into high-dimensional vectors, and these vectors represent locations in space, and we can project them onto manifolds, even simple ones like a hypersphere, and we can take these locations, and hopefully we want to train a model such that the locations corresponding to ideas, the distances between these locations, correspond to the closeness of these ideas. And the way we actually get the model to do these, make these meaningful location representations, is through something called contrastive learning. And the key objective of contrastive learning is to create a sharp contrast between the spatial representations of the positives and negatives with respect to the anchor. So effectively, this means if we have a 2D representation as shown here, we have an anchor, which in our specific case would be the prompt and the context. We want this to be very close to the positive or the correct answer. And during training, we also want to make sure that the anchor is being repelled from the negative, which is the incorrect answers. Now, the way we specifically implemented this in my approach is through polytuplet loss. With this neat little formula here, and this encapsulates all the key ideas of contrastive learning. We can start again with our spatial representations and determine the goals from polytuplet loss. Firstly, that the positives are close to the anchor. Second, that negatives are far from the anchor. But you'll notice that -2 is not being repelled. Why? Because we want positives only to be much closer by at least a margin n to the anchor than negatives. In this way, we are only training to prevent incorrect answers that are too close to the correct answers. So if we already know an answer is very wrong, we no longer need to train that answer to look more wrong to the AI. Now, the way we actually implement this is through a model architecture that looks like this, in which we have our context, which would act as our anchor, and the context question and a singular answer as the quote-unquote result that is passed through as a positive or a negative in the spatial representation. And this may look fairly convoluted here, but we can break this down to the same ideas that I already covered. This chunk right here converts our natural language into the spatial representations. Then once we have these locations, we just measure the distances between the locations in the vectors that we generated earlier. And all we have to do to classify is select the minimum distance. And here we just have the polytuplet loss to ensure that during training, the locations are made more meaningful. Now, the way we verify that all of this theory has any value at all is obviously through testing. And we use the Reckler dataset, which consists of over 5,000 non-trivial logic questions, just like the one that I showed in the sample earlier. And these are drawn from the GMAT and LSAT exams, in which humans have about 60 to 70% accuracy. We used about 90% of the data for training to ensure that the model knows what's going on, and the rest of the data, the 10% that the model has never seen before, is used to generate our results. And here are the results. Across all model sizes, performance improved by about 5.6 to 11.7%. So as you can see, regardless of which of the models that we used for the small and large, we saw noticeable improvement. And even compared to more modern models like the GPT class, Polytuplet remains competitive. And because we used earlier models of the BERT class, they are significantly smaller. But as you notice, the only model that outperforms Polytuplet is GPT-4, which is multiple orders of magnitude greater in complexity and size than Polytuplet. So overall, we can take away a few key ideas. First, that logical reasoning is an important area of AI that needs further development. Second, that multiple choice logical reasoning in particular is a useful baby step to building this stronger ideal AI. And finally, that the artificial intuition idea encapsulated in polytuplet models have the capacity to significantly improve AI performance, and that polytuplet and the artificial intuition is a promising alternative to existing AI logical reasoning. Thank you.